coloring, go ahead and stop coloring for me. Put your markers down. It's like competition. What's the chef show? Chop. Hands down. Plated, right? Okay. Here we go. So we now know that there are these weird locations on the periodic table that are called S, P, D, and F. We're going to jump on those soon. But I want to go ahead and name off 3 rules, at least the names of the rules, why they're relevant, and then we're going to kind of backtrack to something called quantum theory or quantum mechanics. So, Jillian, what was one of the rules that was used to write out electron configurations, whatever those are? We don't know yet, but it's a guy's name. Off-ball, right? Off-ball principle. So someplace on your periodic table, you can write down off-ball, okay? I just want to write down their names first. Off-ball principle, what was another one? Rishi, what you got? Say again? Hund's rule, okay? And I got one more. Shout it out. Polly, okay, fun story. So my big dog, the Great Dane, his name is Wally. And we wanted to name our little dog Polly, because I wanted like Breaking Bad and a chemistry, theorist in there. But then Polly and Wally were too close; they couldn't figure out who we were calling, so we went with Ellie. Yeah. Okay. So off-ball principle, Hund's one's rule, and Pauli exclusion principle. We're going to use those today, so just want to keep those in your brain as we go. All right. Switching modes. Fill out the note sheet that had the wavelength wave notes on it. It says quantum on it. Looks like so on the back of your history notes, looks like this. Okay, so you'll see that I've already given you a lot of information called the modern model, quantum mechanical model. Giving you a lot there. I'm going to add to it by giving you some pictures to draw with that. So make sure you're with me. This is really complex. This is like high-level chemistry and theoretical physics. But I'm going to try to make it as easy as I can for you to understand why we're talking about electron configurations in just a minute. Did everybody find their stuff? Yes? Thank you, Robbie. Robbie found it. Anybody else? You guys are so great today. Oh, so I was talking to Margaret yesterday. On the problem set 5, my positives and negatives on the one that you have on your up from the website are not all the way correct. So I have these here for you. I'll go back at this at the end of the day, at the end of class. You guys can take a picture of this, and I haven't uploaded this on the website yet. But whenever you're doing superscript, subscript, superscript, subscript along these, you'll notice that all the hertz should be a positive, and all the joules should be a negative exponent. But I will put this back up on the board at the end. Okay? So I don't really want to be in your picture right now. Okay. So I'm going to skip the protons for now. We'll come back to that. Let me go here. All right. This is what you have on your sheet of paper. Mostly. And not every bit of this do you have on your sheet of paper, but some of it. So basically, guys, we talked about the subatomic particles. There are 3 of them. What's one of them? Robbie. Protons. Okay, we know they live in the nucleus, right? How? What's another one? Neutrons. Neutron lives in the nucleus. We pretty much know where those are. Like, they can't really go anywhere, right? What's the other one? Electron. Now that baby can go everywhere. It can be close to the nucleus, a little farther away, a little farther away, a little farther away. It can be in different shaped orbitals, and so forth. Now, Bohr said, what were those things called? What are the rings? Orbits, right? Very specific. So Bohr said, we have these rings around the nucleus where the electrons exist, and we're going to call them orbits. But that's only like partially true, because it's only true for hydrogen. They couldn't really justify it being true for all of the elements, so they came up with another theory that further explained where the electron existed. And that's called the quantum mechanical theory. Quantum mechanical model. So that's what we're going to see for the first 5 minutes or so today. And that's what all this right here is saying. Quantum mechanical model. Here we go. So, Schrodinger and all of his crew came together and were like, there's not enough support to say that they live in these orbits. We're going to call them orbitals, and I'm going to be a lot more descriptive on where we think the electron exists. Basically what we're going to do is we're going to say the equivalent of the address of the electron. Okay, so if we all had to say where we live, what state do we live in? North Carolina. Okay. That's kind of the big picture. With an electron, the big picture is what energy level do you live in? Okay, so I'm going to go down to these. which is on your paper. I'll come back up here momentarily. Okay, so for us, North Carolina is the big picture. For the electron, the big picture is the energy level. The energy level is just the distance from the nucleus. That's it. So it's going to be really similar to saying like, oh, I'm in the first energy level, which is right around the nucleus, or the second energy level, which is second from the nucleus, and so forth. Now these look like orbits, but I'm going to draw better pictures for you in a second. So it's really just the distance, but that has a specific name. Principal quantum number. Do you remember seeing N? The letter N? Where did you see that? On the Bohr model. N1, N2, N3, N4, N5, etc. So that's basically all that is. All right, so that's North Carolina for us. That's our state. That's not very specific, right? You're like, okay, we kind of know where it is. Let's get more specific. So then inside of each of these orbitals, inside of each of these energy levels, there are many different shapes of orbitals. So who's already started looking at problem set 5 and you're seeing like SPDF stuff? You just do that for warm-up, right? Okay. So what we're going to now talk about is the shapes of the orbitals that exist inside of North Carolina. So they are called sublevels. They have a fancy name too, angular momentum quantum number, but we're going to really just refer to them as sublevels. They have 4 different shapes. Ready? You're going to draw them with me. The s orbital is a sphere. That's pretty easy. S orbital is a sphere. The p orbital is like this dumbbell thing like this. Like a big figure 8, yeah. So S is a spherical shape.
What are we drawing from? So we're just drawing those, not the bigger.
Yeah, draw this right here for me. I want you to recognize these orbital shapes. Okay, so the p orbital has this kind of shape, but there's actually 3 different ways we could draw that, right? So a sphere, can you draw that in the x, y, and z axis? It's just going to look the same, right? Okay, I've drawn this one in the what axis? Y. Okay, what would it look like in the x axis? Just sideways, okay. And then z axis? So they cross, they actually go out of the board and into the board, but I'm not that skilled, so here we go. So it's kind of like that, and then dashing it back. But really, guys, I'm just trying to show you, they just have this weird dumbbell shape. There happens to be 3 of them, but I'm going to get to that in just a minute. Okay, so we have this S-shaped orbital, we have this P, which I'm going to call the dumbbell. Dumbbell? A pin here. Okay, and then we have, I'm going to draw this in a different color, we have the D-shaped orbitals. They're double dumbbells. They look like a cross. They're like this. Draw that for yourself.
Teachers on the 2nd floor, please put your recycling bins out at this time. Teachers on the 2nd floor, please put your recycling bins out at this time.
Okay, there's a couple different orientations of that one too, but no big deal. We'll get to that shortly. So we have sphere, dumbbell. This is a D orbital, which is a double dumbbell. Okay, and then we have the F-shaped orbital, and it is a flower, like this. You got to be like super skilled. Look at that, guys. Okay, now just draw a bunch of loops together. Looks like a flower. What shape is, or what orbital is this one? So that was S, that was P, this is D, this is F. Okay, so as you can see, the shapes of these orbitals, they get kind of funky, but these are just where electrons live inside the atom. So we did big picture of North Carolina. So what would be a little bit smaller picture for talking about where you live? Okay, the city. Okay, so basically we can start to narrow down. We went from North Carolina down to our city. We could go to Concord, Charlotte, Statesville, Salisbury, and they have these different shapes because cities are different, just like orbitals are different. Okay, so now that we know the shapes, sometimes we have to get really just a little bit more specific. We're like, okay, Charlotte's pretty big. We're in Charlotte, and that's where we talk about the magnetic quantum number, which we're just going to talk about the position that this orbital takes in space. Well, the S shape can't really do anything else. It's a sphere, people. This P one, that's what I was drawing earlier. It can take on this shape, or the orientation, in the y-axis, the x-axis, or the z-axis, and that's kind of what I was talking about earlier. So we're going to move more specific. Are you in this one, or this P orbital? And that's what I'm talking about for Charlotte. Now, if I want to get even more specific, and I was like, I want to know exactly where Risha lives in Charlotte. I don't, but if I want to know exactly where Risha lives in Charlotte, I'm going to go down to his actual, I'm in Charlotte, down to the street, or maybe even the house number, right? So I can get more and more and more specific as we go. So that's where we're talking about electrons, of course. Now we want to know actually how does the electron look in that orbital? And that's called the spin of the electron. And the way we denote that is we say that it spins clockwise or counterclockwise. And the picture that we can put with that is that the electron is spinning up or the electron is spinning down. So if I draw an up arrow, that means the electron is spinning clockwise. If I draw a down arrow, the electron is spinning counterclockwise. So backtrack with me. What's the big picture of an electron where it exists? So the orbitals are not the biggest picture. What's even bigger than just the orbitals? Huh? Okay, yeah, I got them. What's the very first big picture one called? The energy level. That's not very specific. I mean, the first energy level, or the second one, or the third. More specific than the energy level was the style of orbit, right? Or orbital style. So like the shape of it, S, P, D, or F. And then we got even more specific, and we're like, which P orbital, or which D orbital, or which F orbital? And my example of that orientation being X, Y, or Z orientation. Because there happens to be 3 P orbitals. So you're like, which one? That's why you're going through all these orientations. And then what's the most specific we can get? The type of spin the electron has. It's either up or down. Okay, I'm going to let that kind of melt in your brain a little bit. We're going to come back to that when we do electron configurations. Maddie, will you cut the lights on for me? Yeah, what's up, Caroline?
No.
Okay, I want to keep that for a second. So, yesterday we did our collaborative learning. I got a little bit more today. Woo! And this one's a little different. So, you guys have your collaborative groups in front of you, your table groups. And here we go. Kind of get out of chemistry mode. Come back to me. And, oops, let me scooch down. It's frozen. Okay. Again, thank you for participating with positivity. Ooh. This one's called the yes and culture. So I'm going to give you a quick background on what I mean by this. So a lot of times in conversations, in life, and group work, you guys kind of have your guard up. And so Emily's like, no, 2 plus 2 is 5. I'm like, I don't know about that. She's like, well, 2 plus 2 is 4. I'm like, yeah, but why do you say 5? So that kind of confrontation comes out. So you guys are all really high achievers, but I want to make sure that we're all supporting each other in our conversations. And when I say conversations, it might be about chemistry, it might be about something else. It might be in another class, it might just be in life in general. So we live in a yes, but world where you're like, but you're not right, or but how did you come up to that? We want to live in a yes and world where we have to explore others' ideas instead of being so skeptical at first. So we're going to kind of just do a little exercise real fast, and we're going to do it in our small groups. So yes and culture versus a yes but culture. We're going to stand up. Stand up. In small groups. And listen to me as we stand up. So we're basically just going to kind of acknowledge each other. And I know you're going to think this is silly right now, but acknowledge each other. So if I'm in this group of 4 right here, I'm just going to look at Emily. And I'm acknowledging her. And I'm saying and. So yes and we're just going to switch spots. Because I'm acknowledging her, and we're switching spots, and I've allowed for her to kind of take the lead. Now, after Emily, I'm going to do that with somebody else. Because I already did it. I'm no longer allowed to be yes and. Okay, so I just want you guys to look at each other, acknowledge each other, switch spots. Take 2. Go ahead.
And you're sick.
Wait, do we switch?
Yeah. What?
So I did a little wrong.
You're Indian. Wait. I've already done every one.
All right, and sit back down for me. Sit back down. All right, eyes back up here. All right, so that was just really simple. You're just acknowledging somebody. I mean, I don't know about you, but I like to look in each other's eyes when I talk to them. Are you guys that person? Like, okay, whenever, as a college student, I would, to really stay engaged, I couldn't like be out in level land. I had to look at the presenter, my professor, and I would creep them out. So like stare at them the whole time. Like, why is this student staring? That's just how I pay attention. So if I'm looking at your eyes, I'm paying attention to you. That's a good thing. When you're looking into my eyes, I expect that means that you're paying attention as well. You don't have to look into my eyes, but that's okay. So basically, whenever we're going through this exercise, what you're thinking, what you should be kind of acknowledging to each other is that I see what you're saying, but I want to add this. There's no but there. So if Jillian's telling me something and I agree, but I'm still like a little hesitant, so I'm going to ask you what you're saying, but what can we add, or is there anything we can add here? So it's not so skeptical. You're kind of empowering each other to grow together. That's basically all this is. So we kind of just did the little yes and we walked around. We did that. So where would we use this? Where we would use this just in general is using stems like this. So on your desk there should be a packet, and I quickly went through the beginning of this, but I want you guys to look at the stems. This is just like phrasing, and I want you to think about where we would use this acknowledgement system, this method of acknowledging each other, saying yes, and let's explain this idea more. Yes, and I need to check for understanding just a little bit more. Yes, and I need some clarification. Or yes, and I need to get unstuck. So talk about where you would find this useful in our class. Go.
When you're doing a lab and you're like doing something like that, yeah, actually did as you start chasing clean ideas, you don't know. You think you know, how they clearly something new. I might. Oh, I think really didn't see you doing it. I thought you were actually asking how much you consider so we're not going to see how I'm like. Oh, he's like it's a fraud. It's fraud is stuff.
Are you guys done? For now? All right, eyes back up here, 5, 4, 3, 2, 1. All right, perfect. So I'm going to work with this group. So example from yesterday, I saw in the lab. Yesterday we talked about kind of the group contract. What are you going to do if you are participating, and what are you going to do if you're not participating? Kind of have that respectful conversation with each other. So if I'm like, Caleb, I don't know how to use the spectroscope. What would you do with me? What would you, like, you should be like, sorry, you don't know how to do it. You're SOL. What are you going to do? Well, which one? Are you going to explain ideas? Are you going to check for understanding, ask for clarification, or giving insight? Okay, so he's probably going to say, oh, okay, well, this is just a device. We're going to hold it up. We're going to look for light. And then as he's holding it up, and this is what I try to do with some of you guys, as he's holding it to light, and I'm holding it to light, I'm going to say, or he's going to say to me, all right, so I see you're holding it to light. Do you see that orange one? Yeah, I see the orange one. Okay, do you see where it's at? Oh, it's on 7. Do you know what that means? Just kind of being helpful. And what does that 7 mean on the spectroscope? 7 Not 7 angstroms. 7,000 angstroms, right? And then what do we have to do with that? Convert it to meters, and then what do we do with that? Found the frequency, and then what do we do with that? Found the energy. You guys got this flow. Okay. All right, thank you. I have one more thing for you for this particular activity. So actually, I think I'll hold off on that. We'll hold off on that. All right, back to chemistry. You ready? Back to chemistry. That's it, guys. That's it. That's all, folks. Alright, so as we're going through today, as we're going through some of the books and some of the problems we're doing today, I want you guys to use that method where you're helping each other in that kind of direct manner. Alright, so we talked about the quantum model. Sometimes, instead of calling them electron energy levels, we'll call them electron clouds. It really is the same thing. It's just where does the electron exist. So let's learn how to use this. Let's learn how to use this. Oh, there's my pictures. Versus drawing them, guys, look at all these orientations. Look at these crazy orbits. I'm going to clap on. Okay. So look at the very first one. What's that one?
Sphere.
That's the sphere, right. Look at the p orbitals. You see there's one that's in the x, y, and z, and then all together they look like that. Okay. Look at the d. The double dumbbells, how many different orientations are there? 5 different orientations. As you're going, you're thinking s orbitals, there's only one style of orientation. P orbitals, how many styles of orientation? 3. 1, 2, 3. Right, there's 3 different styles of that orbital orientations. For the d block, how many? 5. And then can you guess what this trend, what the f block orientations would be? 7, right. 1, 3, 5, and we added 2 more. 7. Okay, what if I told you a secret? So that orbital, let's say this crazy donut one right here, okay? That guy can hold 2 electrons. That's it. How many electrons can the s orbital hold? So sorry, the rule of thumb is every single orbital can only hold 2 electrons. That's it. So, s orbital, there's only one of them, right? How many electrons can that hold? 2 electrons. Okay. How many can all the p orbitals hold together? 6 electrons. Okay. How many electrons can all the d's? 10 electrons. And f, 14 electrons. All right. I want you guys to think about electrons as they build. So if I said find sodium, you guys periodic table out? Okay. You got sodium. How many electrons does sodium have? Find sodium. Raise your hand when you know how many electrons it holds. Emily, how many electrons does it hold? 11. So let me scooch to actual periodic table. I swear I have one. Okay, here we go. Sodium has 11 electrons, right? Well, those 11 electrons don't just all clump together. They live in all those different shaped orbitals that we had just talked about. But they build slowly. They can't just pop out of the p orbitals. They build slowly. Some go in the s orbitals, some go in the p orbitals, and some are in the first energy level, some are in the second energy level, so there's a layering system here. So if I went further, and I was like, okay, how many electrons does magnesium have? How many electrons does magnesium have? 12. So its electrons that, as they're configured around the nucleus, can look a teeny bit different than sodium's. So now we're going to talk about how do we write out the electron configuration? How do we tell where these electrons exist? So let me show you. I think I'm good there. Okay, this is maybe what you guys have seen before. Who's sure? Give me a thumbs up if you've seen this. Have you ever seen anything like that? Like you drew the little dots around the nucleus, like in middle school? Yeah? Lies, flat lies. Okay, they can't blow your brain up in middle school because then they'll never get you in high school, right? You'd be long gone. So they tell you this to tell you generally where the electrons exist, but it's a little bit more detailed than that. So most of you guys are like, yeah, there's 2 electrons in the first energy level. How many in the second energy level? How many in the third energy level? 14. Well, okay, there's 14 here, but upwards of, what's the max? Do you guys remember that? 18? 18? So let me tell you why that first energy level can only hold 2. It's because the first energy level only has an s orbital. How many electrons fit in that s orbital? 2. Okay, what if I told you the second energy level, has an s orbital and a p sublevel. Okay, how many electrons fit in the s? 2. Okay. How many fit in all the p's? 6. Do you guys remember that? You just did 1, 2, 3. That's 6. Guess how many 2 plus 6 is? 8. Okay, so that detail is not what we're going to get into. I'm not going to get 18 right now. So here's what this looks like. Oh, I'll come right. Oh, I guess I will. No, I'll show you this now. Here's what this looks like. Whenever we write this down right here, okay? Whenever we write down an electron configuration, we use a code. We use a number system to say what energy level it is in, what sublevel or orbital it's in, and then how many electrons are there. So we have a special code. I'll let you guys read and write from it. Are the lights off okay? Yeah. I know my board's a little hard to see if the lights on. All right, so the special code. Now you guys are going to be in the secret society of chemists, okay? The energy level, which is either n is equal to 1, n is equal to 2, blah, blah, blah. That is going to be this big, huge coefficient right here. So the energy level is represented by a coefficient. So that's telling you this electron that we're talking about lives in the first energy level. The shape, of course, of the orbital has a letter associated with it. So the type or the shape of the orbital, which is what we called sublevel earlier, that's represented by the letter S. So what shape is that one? A sphere, right? Okay? And then how many electrons are in that orbital or in that sublevel in general is represented by this exponent up here, that number. So what I'm telling you is that this particular electron lives in the first energy level in the S-shaped orbital, and there's only one in there. So we can go a little further, but if I told you that I only had one electron total, who would I be? I would have to be hydrogen, right? This is the electron configuration of hydrogen. This is it, 1s1, boom. Find hydrogen on your periodic table, point to it. I really actually want you to touch hydrogen. All right, what block are you in from your warm-up? S block. What period are you in? 1. How many elements over into that period are you? 1. Okay, so you guys just told me you were in the S block. You're in the first period, right? So period is the same thing basically as energy level. And you said you were 1 electron over. All right, let's go a little further. I want you to find helium. Now I know helium is over there on the very right-hand side. Can you guys scratch it out there? Scratch it out, and I want you to do this. Put it right there for me. Yes, ma'am. Yes, and just, yeah, I think I'll do that first. All right, so if we are here, because helium is so tiny, it can't accommodate many electrons. How many electrons does it accommodate? 2. That's it, 2 electrons. So we're now seeing that it's in the S block, right? So I want you to put S. Was it in the first period, or what period are we in still? We're still in the first period, so that's 1s, right? And then how many electrons over into that period are we? 2. 1s2. That's the electron configuration of helium. 1s2. 1s exponent 2. Yeah.
So, like, why is it not on that side but over here?
Because it's a noble gas. Technically, it has a full energy shell, which is 2 electrons. But because it's so small, it's more similar really to hydrogen than necessarily all the noble gases, which are in group 8. So we're putting it here just for electron configuration purposes. That's the only time. Yeah.
So because it's in period 1.
Period 1. The big one. It's in the S block, right? S block is this entire section. That's why I get the S. And then how am I getting the 2? 2 electrons over into that S block. All right, I'm going to make it more complicated. Over, so it's like 1, 2. So there's 2 electrons total, because helium doesn't come without having already basically building hydrogen. You have to have 1 electron in first, and you put the second electron in. Yeah.
Why is that not the element number?
I will tell you why in a minute, because the element number is talking about protons, right? Not necessarily the arrangement of the electrons. We're really getting into the nitty-gritty of the arrangement of the electrons. How do they live around the nucleus? Yeah.
Is that because there are ions?
Yes, we're going to get to ions shortly, but yeah, the electrons can change, so that's why it can't just be its atomic number. Good job. Yeah.
Because in Z block, would it be 3 because it says
N minus 1.
huh?
Oh, I haven't gotten that far yet. Give me a second. Okay. So before we move to drawing and writing more of these, those rules you told me. Off-ball. Who else? Huns and Polly. Okay. That's what I want to review before we start building more and more elements. So off-ball's principle. You guys wrote this down on your reading guide, but I'm going to make this easier for you. Whenever we put electrons into the atom, we're building this huge electron cloud. We always start at the lowest energy level first. That means the lowest period, which is, of course, n is equal to 1. So I like to call this off-ball, awfully low. So, you know, I like to come up with really stupid ways to remember things. This is how I did it when I was 15 or 16, so whenever I took chemistry. So off-ball's principle, awfully low. Start off at the lowest energy level. Pauli exclusion principle. Pauli pairs. Electrons can only exist in a pair, meaning up to 2 electrons in any orbital. And that's what we were just talking about. S had the ability to contain 2 electrons. P as a whole had the ability to contain 6 electrons. D as a whole, because there's 5 different shapes of those orbitals, can contain 10, and F could hold 14. So they can only be appearing in pairs. So let's say I had an upward spinning electron, or sorry, a clockwise and a counterclockwise. What I would draw was I would draw 2 electrons just like this, spinning up and spinning down. That's it, and that's in an orbital. So what I'm drawing there is the line below it is the orbital, and these electrons are depicted as a spin up and a spin down, or a spin clockwise and a spin counterclockwise. We're going to be drawing these shortly. All right, so off-ball, awfully low. Pauli pairs. You can only pair up electrons. You can't put triplicates and quadruplicates and all that. You got to go up to 2. And the last rule I like to call Huns-Wun's rule. Meaning, electrons don't really want to be next to each other necessarily. Why would that be? Electron right up next to another electron.
They have the same magnetic charge.
They have the same electronic charge, right? They have the same negative charge. Negatives and negatives don't really like to be together. So if we can avoid putting them together, we will. And that's what Huns-Wun's rule does. You put in 1 electron per orbital time, and if you've got to double up, you can go to pairs, and that's it. Yeah?
Not sure that I understand pairs.
So I'm feeding you bits and pieces at a time, but I'll draw you a picture for this one, okay? So Huns-Wun's rule means that if I have the p orbital like this, and then the other p orbital, which is the z-axis, and I'm putting in electrons, I got all these p orbitals available to me, right? Let's say I want to put 3 electrons in the p orbitals. How would I file them in here? I'm not going to put 2 electrons in here together. That would be dumb. They're 2 negatives. They don't like to be close to each other. They repel. So I can't put them in there together first. I have to follow Huns-Wun's rule. I do 1 electron, another electron, and another electron. 1, 1, 1. And if I have to, let's say I had 4 or 5 or 6 electrons, if I have to, I will go back and fill them in the other ones. But my first goal is to separate them. That's what I mean by pairing. And I'm going to draw those better for you momentarily. Yeah?
So in the first orbit, or the first orbital, can there only be, you said that only 1 per orbital if we can.
Yes.
If we have 3 electrons, do we put 1 in the first orbital and then try and go out?
I want to demonstrate that for you in a second. Okay? So I'm going to wait on questions for a moment because I would like to go ahead and give you more examples. So I think that'll clear up a lot. Okay? All right. And you ready? Okay. So here is oxygen. I want you to write down an example of it. And I'm going to show you from your periodic table how does this work. So oxygen's electron configuration is 1s caret 2. Lindsay, with me? You good? 1s2. Make this a little bit bigger. 2s2 and 2p4. 1 second. Wait, like I said, I'm going to give maybe 5 minutes for questions at this point. So after you've written this down, I want you to point to hydrogen on your periodic table. Alright, so we can't just straight up jump to hydrogen, oxygen when we're building an atom. You have to file it in electron by electron, period by period, sublevel by sublevel. So the way we got here, and I'm going to use my periodic table because I can't do this with a periodic table, I'll show you this. The way we got here is we built from hydrogen all the way to oxygen over here. So how do we get there? We went through the 1s sublevel, so that's where we got 1s, but there were two elements in the way, right? Hydrogen and helium, so that's 2 electrons over, so we did 1, we were in the s block, and we put 2 electrons in, so that covered all the 2 electrons that will fit in the 1s. All right, so we essentially covered the first energy level. Then where do we go? To the second energy level, so that's where I got the 2. I went all the way through the s block, so that's 2s, 2, because I went 2 electrons or elements over. Now I'm over here in what block? So I'm in the p block, but am I still in the second energy level? Yes, so I'm going to put 2, and then I'm in this whole entire block called p. But how many electrons or elements over did it take me to get to oxygen? 4. 1, 2, 3, 4, 2p, 4. Okay, now here's how you double check. These guys up here, these 2, 2, and 4, what are those representing? So the amount of space we get, but what did we say earlier that those little exponents represented? You wrote it down. Number of electrons in that orbital, right? So overall, oxygen has how many electrons? 8, right? So atomic number 8 has 8 electrons. 2 plus 2 plus 4 is 8. Your exponents add up to all your electrons, because basically all we're doing is mapping out where the electrons exist in this humongous electron cloud. All right, let's do another one. And I'm going to go back to something called orbital diagram. Let's do another one. Let's do calcium. You guys follow along the periodic table, row by row, and I want you to write the electron configuration for calcium. But before I answer questions, I want you to try. You guys have your nice colorful periodic table to help as well. Give me a thumbs up if you're okay getting started. I don't see a lot of thumbs up, so let me help on the first one here, okay? So you guys tell me, if we have to get all the way down here to calcium, how many energy levels are we going through? 4. 1, 2, 3, and 4. But we actually have to count for every electron it took to build up to calcium. So here we go. You ready? Remember, helium is here. It's a part of S block. So I'm going to write it at the top because I don't have a lot of space. So as I go through this whole entire section, what have I accounted for? 1s, 2. Okay, done with the first energy level. Great. Now let's go through this block. What is that? 2s, 2. And that gets me through to beryllium. And then I'm going to go all the way over here, get me through all the way here. 2p, good, 6. 1, 2, 3, 4, 5, 6. All right, and that gets me to neon, right? Okay, now I'm going back down here, get me through 3s2, okay, and then, so we're still in the third energy level. We happen to be in p block at this point in time, and there's 6 elements or electrons it took to build up. So now we're at argon, right? All right, now get me down here to calcium. 4s2. All right, before you even count electrons, how many electrons should there be here? There should be 20, because electron configuration, or the element number of calcium is 20. And we count 2, 4, 6, so that's 10, right? And then 2, 6, 2, another 10. So total, we have 20 electrons. Yes, ma'am. Give me 1 second, okay? So here we go, guys. Let's write out sulfur. You guys are going to write out that electron configuration. Write it out. Talk to your group members.
Sulfur is 16.
guys. All right, do I have a confident volunteer? Go for it, Darcy. 1S2. 3p4, because we stopped at sulfur. Right, okay. How many electrons are here? 16 total, 16 total. Give me a thumbs up if that so far is making okay sense to you guys. All right, I got a large portion of you guys. I'm going to keep going and give you a couple more examples. Now, this is called an electron configuration, okay? Now we have something that's really, really similar, but it's called an orbital diagram. It's actually a picture. We're drawing a diagram here. So you guys have your calcium one, right? I'm going to go to some space here. I'm going to put this for calcium. And here's how you depict it. You draw little dashes like this to say it's an orbital. And you draw the electrons spinning up and down to talk about the electrons. So for calcium, you guys had what? 1s2, 2s2, 2p6, 3s, 2, 3p6, 4s2, yeah?
Yeah.
Okay. This I'm going to call the first orbital 1s. 2, and I'm just drawing half arrows because I'm a little lazy, so those are 2 arrows, 2 electrons. So 1s2. You got me?
No.
So I'm labeling, this line right here, I'm calling an orbital. I'm labeling it the 1s orbital because I'm using the 1s orbital here. And this tells me there are 2 electrons in the 1s orbital, yes? So I'm drawing 2 electrons to say I have 2 electrons there. Those are arrows. Those are arrows. There's half arrows, but they're arrows. Give me a second, Caroline. Okay, so if I asked you now to draw the 2s orbital, what would you draw? So you draw a dash, and you label it 2s, and then how many electrons go into the 2s orbital? 2. Arrow up, arrow down. Remember, electrons have to spin oppositely. They can't spin the same way. They have to spin opposite. Okay. We've gotten this part done, this part done. Now I've got p orbitals, right? Now, the p sublevel, just p in general, how many orbitals were there? 3, x, y, and z, right? I have to draw 3 dashes. 1, 2, 3. I have to. Because if not, I'm lying. Because remember, there are 3 different orientations of the p orbital, x, y, and z. So I'm going to label all of these just with a bracket as 2p. And I'll tell you why in a second. Because I don't want you to write 2px, 2py, 2pz. That's just too detailed for us right now. So there are 3 orbitals. Now I need 3 orbitals because how many electrons here are here? 6. And I can't put more than what? 2 per orbital. Now, here's our rules. Have we started at the lowest energy level so far? Yeah. Whose rule are we following? Awfully low. Okay. Next is like, okay, poly pairs, right? Pairing up. We'll put them in electron spins opposite. What's the other rule? One's rule. Okay. This is where we have to use that, and it's just me demonstrating it for you. Hund's one's rule is you put 1 electron in each orbital, and if you have to go back and pair, which we do, we got to get 6 in here, guys. If you have to go back and pair, you do. Pair, pair, pair. Total, I have 6 electrons, right? But I followed Hund's one's rule. This one I wouldn't know if you did or not. But later on, I'll know if you followed it because you'll have the mistake at the end, and I'll know you weren't doing your Hund's one's rule. We'll get there in a second. Okay, so far I've gotten 1s2, 2s2, 2p6 taken care of. You guys tell me what I would draw for 3s. Darcy. Okay, an arrow up and down because there's only 1 orbital here. We got to put both of them in there. All right, somebody at that table, Julian's table here, tell me what I would do for the 3p. 3 dashes, and then what? So label that 3p as a total. And then put another electron just to double up, right? Ooh, my board. Oh, okay, there's 6 electrons there. All right, so I've now put 1, 1, 1, and then I doubled up 1, 1, another 1, because I had to get a total of 6 electrons in there. Now I'm on the last one, guys. What do? 1 dash, label it 4s, and so 1 up and 1 down, or down and up, whichever way you do it. So that's basically a picture. All of this is just a picture of our electron configuration. You see that they're basically exactly the same thing. One's a picture, one's just written. Yeah.
Do you always have to start with block one?
No, you can do whichever one. I just tend to have a similar way of doing it. Yeah.
So the way that we like actually draw like with the circle.
With the circles,
Yeah, so like how would this be represented in
you would have two electrons in the first energy level. You'd have 8 in the second energy level orbit, and then you'd have 8 actually in the next one. But I never ever want you to draw that way, ever. Yeah.
I mean, I know you just said you don't draw it like that,
Mm-hmm.
but you have to group those together, then how?
You don't group them together. We are being more specific now. I'm literally asking for how many are in the s orbitals, how many are in the p ones, how many are in the d ones, how many are in the f ones. So we don't want to group them together. We want to say there's this many here, this many here, this many here. We're just being more specific than we've ever been before. Okay? Give me 1 second. So I need to teach you how to do a d orbital one. Let's do this last one together, and then I'll let you guys work some. Because I feel like this is me talking a lot. I'd rather you guys work together a little bit more. So let's go crazy, guys, and let's go down here to cobalt. So I want you guys to go ahead and write out the very first part if you can, and then I'll help you when you get to D block. Go down to cobalt. It's in the middle of D block, right here. I just want you to write out the electron configuration. No orbital diagram right now. Electron configuration. How far have you guys gotten? Okay, I'm going to tell you a second rule of thumb. So you got your 4s2. Thumbs up. Cool. Okay, so here's the caveat. D energy levels, D block in general, they're this weird in-between phase of energy. They're not 100% in the third energy levels of total or the fourth. They have a little in-between. I'm going to show you what that looks like before I move on. So it's called the off-ball, right? Start off awfully low. It's called the off-ball diagram. And I would never have you draw this, never have you memorize it, but I want to show you this proof of concept before we move on. So we all know you start with 1s, right? Then you got a 2s. Then you got a 2p. We're going in order of energy, right? Then you got a 3s. Then you got a 3p. Then you got a 4s. And then what? 3d. See how that 3d is right kind of between the 3 and 4? So that 3d is actually a little tiny bit lower in energy than the 4p. So we have this rule that we employ whenever we're looking at the periodic table. So on your periodic table, the one that you colored, I want you to write down the rule, and it's only for D block, only for D block. You do n minus 1. What does n mean again? Energy level, right, or period number. Basically, in this case, the same thing. So so I know we got to 4s2, yeah? Don't say 4 here. When you hit D block, what do you have to say instead? 3. You're doing 4 minus 1 to get 3. So n minus 1 is that rule. And I'm going to tell you another secret. Get down to F block, which we might get to shortly. You do n minus 2. So energy level minus 2 periods or energy levels, and that will give you the correct levels of energy according to the off-ball diagram. So this is me helping you so you don't have to memorize the off-ball diagram, because nobody's got time for that. Okay? So now we have cobalt, right? Cobalt's like here-ish. Let me go back to my periodic table. There's cobalt. So we got to 4s2. Now what would you say? 3d what? 7. 3d 7. 1, 2, 3, 4, 5, 6, 7. Okay. Now, I'm not going to make us draw the entire orbital diagram. Yeah, what's up, Lindsay? Because see this, we went from the 4th energy level, and then instead of putting 4 there, we put 3 there intentionally, because the third 3D energy level, or sub-level, is a little bit lower energy than 4p. Okay, so here we are. Yes, ma'am?
I was still not understanding why you.
Drop energy. Why I dropped that number? So I went in order 1, 2, 3, 4, and then I went back to 3. Is that what you're asking?
No.
Do me a favor, write down your question, because
I'm not sure what I'm questioning.
So then when you figure it out, write down for me, okay? All right, so we know how to write these. 1 has 2, 2 has 2, 2p, yes? How do you draw the p orbitals again? 3 dashes. Okay, you know 3 s we draw 1 dash, 3p we draw 3 dashes, 4s we draw 1 dash. Okay, here's how we draw the 3d. So our d block in general. How many orbitals were in the d again? 5, because 5. 1, 2, 3, 4, 5. They went 1, 3, 5, and 7. Okay, we are going to draw 5 dashes here to represent the 5 orbitals that D block has. So these get kind of big and lengthy, right? So this is all called 3D. Draw this example for me. I have 7 electrons to account for, yes? Okay, 7 electrons. How do I file them in here? Okay, Hund's ones rule, right? So 1, 1, 1, 1, 1. Okay, so I got 5 so far. Then what? I put 2, right? Because I'm only done 7, right? So 1, that's number 6, and another one down, that's number 7. That's how I'll know if you're following Hund's ones rule. Because if you put 7 in there just up front, your first 3 orbitals will be 100% full, yes? You have one little lonely one. But that's how I really can know if you're doing it right. So, do you guys have problem set 5 available? Yes? I'm gonna instead of giving you more examples of mine, I'm gonna give you examples for your homework. Yay! If you take your phone out, that's fine. I'm gonna pull up the problem set. And I'm gonna help you guys more, but I'm gonna give you about 10 minutes by yourself first.
Are we gonna do the test?
Yeah.
Tomorrow?
Today.
Oh, that's what that all meant.
Yes.
I can see that chart again with like the energy levels. Just take a picture of it.
Give
So
me a second. Yep. All right, guys. Right now, I'm gonna give you 7 minutes. But guys, listen. That's why you're in your groups, and I'm gonna come around and help you. But I think some of us get it. I'm gonna let you enjoy this 7 minutes. Get number 3 done. You're gonna write the electron configuration and draw the orbital diagrams for carbon, sulfur, potassium, and argon. I'm coming around. Please raise your hand if you need me. But have your questions ready.
Yeah, it should be 2. And then we have to write out the that's a tough down again. And then yeah, that's 3 dashes. I'll find out what S is. S is wait, you already did the E one. It's like time out. Yeah, we already did it.
No, sorry.
Okay, there's three actually. Okay, so for acids, there's only one. Keys, there's three. So just start the acid one or
I know I said it was but I thought it was
wait, so acid one.
I know a lot of
Yeah, there's it's acid and there's one down. D is 5. D is there's one down.
If that's what? Yes. I don't know. Are we talking about T?
K is potassium. I'm fine, K. K is potassium. It is ammonium. Oh, it is pretty. Oh, yeah, that's D is 5. That's 5.
He has 5.
Yeah.
Yeah.
Potassium.
Well, I mean, I want to. If you want to skip.
All I have is like in my head. 3, 4. Oh yeah, that's potassium. That's the number makes sense. Where have you heard that before? Oh wait, it wasn't an element or whatever that's like would be points. That was the whole thing. Carbon-19. I'll find out the card and I'm not possible. D is
If you don't have very much, let's say this one.
I don't.
You should have a, I think I covered the one that you just have this is not the one that you colored, I just wanted to link. I have a copy of it. Yeah. This?
yeah. Wow, that's pretty cool.
Alright guys, eyes back up here in 5, 4, 3, 2, 1. Okay, so I just had a couple great questions. Carbon, I'm just going to draw carbon. 1s2, 2s2, 2p what? 2. I know you can draw your orbital diagrams for the first one, but when you get to p, yes, absolutely. I don't care if you're using them all or not. You must draw me all 3 orbitals to say there are 3 orbitals available, but there's only 2 electrons, so you're only putting 2 electrons in there. And that's because what you're able to say is, Rushi, how many more electrons can fit in the 2p orbital? How many spaces are left? How many more electrons can fit there? How many electrons can fit here? 2 plus 1 here and 1 here. So there's empty space for 4 electrons that go in and bond or help carbon get to something called octet, which we're going to get to later. But that means there's space. So you need another space. And if you don't draw them, sometimes it's really hard to tell their space. Okay, do me a favor. I think everybody drew what? Sulfur, right? Did you guys
Yeah.
get to sulfur on your electron configurations? Okay, so we got to sulfur. I'm trying to do about 3 more things before we go, so work with me here. Sulfur was 1s2, 2s2, 2p6, 3s2, 3p4. We got that far. We did that one twice in class now. Now, on your orbital diagram, how much space is left for electrons? 2. Does everybody see there are 2 spaces left for electrons? Everybody need that head shake? Yes. Okay, we see there's 2 electrons, or spaces for electrons. Well, guess what, guys? Sometimes ions form. We know that. We know that if you gain electrons, what charge do you become? Negative. You lose electrons, what do you become? Positive. Okay, so what if I told you sulfur gained 2 electrons? So in this little P1, 2, 3, right here, where you had 1, 1, 1, 4, 5, oops, sorry, 4. You have this, right? And I said sulfur gains 2 electrons. Where would you put them? Into the empty spaces, right? Okay, so I'm going to put that in a different color. I'm just going to draw them pointing down. So now I've added 2 electrons. Woo! What's my charge?
-2.
-2. We just made an ion. Okay? So whenever you see on your problem set a couple of ions, I don't want you to be confused. Let's do one more together, though. Yeah.
That's all. If you add 2 electrons, that's now going to be argon.
So this is a really good point. Okay. He said it's going to be argon. Remember, do electrons tell you your identity?
So no.
No, protons do. So if I change electrons, am I changing my identity? No. But what he's saying is that this has the electron configuration of argon, which is important. So if I said what ion has the electron configuration of argon, you could say sulfur 2 minus. You might say something else. So do me a favor. Do magnesium 2 plus. I'm coming around for help. Start off by doing straight up magnesium. Just plain old magnesium. And then put it in front of your electron configuration.
No. Where's magnesium? Because then you can all get
We can just do the electron configuration for Maxwell.
Magnesium's full, by the way.
Alright, eyes up here. Give me a thumbs up if you just straight up did magnesium like this. 1s2, 2s2, 2p6, 3s2. That's straight magnesium. How many electrons are here? Total electrons. 2 plus 2 plus 6 plus 2 is 12. Okay, now let's become magnesium 2 plus. What happened? Okay, so you're saying you lose 2 electrons. Okay, we're going to have to lose them from a very particular area. Remember, this was built from the bottom up, right? From the inside out. Which electrons do you think are easiest to rip off?
The outside.
The outside. Okay, the outside has a name. Lose 2 electrons from the valence shell, or the valence electrons. That just means outer, the outside. Okay, guys. Who's the outside here? 3s2. It's pretty easy to tell because this is the first energy level. These are in the second energy level. These guys are in the third energy level, which is the outside. And there's 2 electrons there. What? Those are gone. That's it. So, you drop those 2 electrons, and with it, the whole entire third energy level disappears. Don't put 3s, 0. Just knock it out. Now, who does this look like? Whose electron configuration does it look like?
Argon.
Neon, right? 2, 2, 6, that's 10 electrons, right? That's neon. So what are you seeing is the trend here? So earlier I knocked out what? Sulfur. I made it sulfide with a 2 negative charge. Who did it look like? Argon. Okay, and this one looks like? Neon. Okay, so where are these existing when they lose or gain electrons? Where are they ending up? Say again? But what specific other elements?
Noble gas.
Say again?
Noble gas.
The noble gases. Okay. Guys, everybody wants to be like the cool kids. The noble gases. It's not just willy-nilly. Oh, I think I'm going to lose 1 electron. I'm going to lose 7. I'm going to gain 10. You can't go willy-nilly. It's a very, very peculiar, specific number of electrons you will gain or lose. So, if I am oxygen. All right, you guys look at oxygen. I'm pointing over here on the periodic table. Am I closer to neon, helium, or argon based on the number of electrons it takes for me to remove or gain?
Yeah.
So am I going to lose electrons? Gain how many? 2. Now I'm going to say 1, 2. Okay, so what's that charge? O2 minus, right. Okay, so if I'm lithium. Okay, I'm lithium. Am I going to gain 1, 2, 3, 4, 5, 6, 7 to look like neon? What's closer for me to do? Lose 1, and as I go from lithium, I back it up to helium. That loses 1 electron. What's the charge of lithium if I lose 1 electron? 1 positive, okay. But it's easier than that. It's easier than that. They all live in the same group, right? They all live in the same group. So, commonly, where's my eraser at? There it is. Okay. Commonly, what you guys are going to be seeing is that anybody in this group here, nitrogen's group, what's it going to do? Is it going to gain 1, 2, 3 electrons to look like the noble gases? Or is it going to lose 1, 2, 3, 4, 5 to go back to the noble gases? Gain 3. So if I gain 3, what's my charge? 3 negative or negative 3. Okay. That's everybody in this group here, because they all have a similar electron configuration, the N part. So now you guys tell me, everybody in this group here, in beryllium's group, what are they going to do? 2 what? Because they do what? Because they can't, I mean, that's like miles away, right? You can't go forward to gain that many electrons. They're going to bounce back 1, 2 to look like the noble gases. So they lose 2, so that gives them a +2 charge. All right, that's a lot at once right now. Okay, so I'm going to give you guys a couple minutes to ask me questions on problem set 5. You guys have about 5 minutes left in class. I already had about 3 questions, so I'm going to answer those first. Somebody asked me, how many orbitals are in each of the following sublevels? What do I mean by this? This means, guys, tell me, look at P, D, F, and S. How many orbitals are in the P sublevel? 3. How many are in D? 5. How many are in F? 7. How many are in S? 1. 1, 3, 5, 7. That's all it means. That just means, like, how many dashes did you draw? I'm going to leave you alone and let you guys do it first.
I knew it. How many organs? 14. Then there's a 53. Oh wait, no. Wait, this one? Because I already did that. What is principle called? Have you done like number 2, like the second question? No. Is B down? Wait, so you still do 2? I don't know, I'm not doing it. Oh yeah. Oh wait. Question 3, why is it not like she's just like, oops. Well, I mean, I guess that helps you, so that's probably why. What's that? The original problem is like this.
The leg has the
Like that's all the numbers.
the Latin I don't know, it's funny.
No, we just identify the other. He's a full 3 energy level. Yeah, I don't know that first question.
Yeah. Not easy down here. So you do walk again. There's 10 electrons across with you, right?
Yeah.
How many orbits are on it?
Oh, 5. Also, when number 2, if you take the whole third energy level, is that like 1, 2, 3 over?
Third energy level is everything that's got a 3 position.
Oh, okay.
So that would be, I'm looking over there, you see the other one?
Yeah.
So 3S is full, 3P is full, and 3D, remember that's D block where you would drop in the light, you would drop in the energy levels, and 3D would be same.
Okay, so multiple. There could be multiple on that one.
Not full, 100% full would be all the way to the very end of D.
Everything.
So I got all the electrons in the entire third energy level. So that's all the way to the very end of D block, which is D.
Thank you.
You guys bring to